All right, welcome to another IAEI News Live. My name is Thomas Dimitrovich, and today's discussion, we're going to kick off Electrical Safety Month with a discussion around shock. And it all starts now. All right. Well, I can't believe it's May. I mean, this year is flying like mad. And the Electrical Safety Month is, it occurs, this focus on electrical safety occurs every year for the entire month of May. And we've got a great lineup associated with these, the topic of electrical safety. Today, we're going to be talking about shock. And I believe next week, on Tuesday, if I'm not mistaken, we're going to have Siemens in, who wants to talk to all of you about this new technology around arc fault circuit interrupters, AFCIs. Now, we all know that AFCIs, I mean, that's a dull topic, right? But I think you're going to enjoy our discussion next week as well. So this week, I want to focus on shock and electrocutions and all of that stuff that influences change. Hopefully, it changes how we do business, changes how we operate and function, but awareness of the hazard is the first step in success, and that's going to be our discussion today. Like I said before, this is a recorded session, and my name is Thomas Dimitrovich. So let's get this discussion started. First off, I put some links down below. One of them is on from the Electrical Safety Foundation International, ESFI. They have a very good resource that speaks to Electrical Safety Month. And there's a lot of resources that you and we and I and all of us can use as we talk with homeowners and customers and others that need to be aware of electrical safety. And that's the other thing I want to make sure I hit, that electrical safety is not just about us understanding the topic. It's not just about us being aware. We need to share our information. If we want to change a culture, we have to speak outside of our normal business. Make sense? All right. So let's talk. Electrical safety. I just had to fix my screen. So if there was a little blip, I just hit pause. I went back, fixed my green screen because it was giving me a line and I couldn't have lines. All right. So this is the website for that ESFI brings to us. And as you can see, it talks about home safety, workplace safety, disaster safety, kids safety, programs and initiatives, and then there's a resource library. There's a lot of materials that ESFI brings to the table and that you need to know about. There are some things that you can download and give to your homeowners or give to the business owner, the facility owner, to raise awareness around electrical safety. Leverage these resources. There are smart homes, safe and secure. There's a video that you can watch. There are net zero energy use resilience, benefits of electric vehicles, energy resilience, energy storage systems, and photovoltaics, understanding surge protected devices, a survey, workplace fatalities and injuries. So this is a survey. This data right here is important because when you think about electrical safety, and we're going to talk about this, we're going to talk about risk. And what risk is, likelihood and severity. I can help you understand what severity is. I can tell you if you get electrocuted, it's death, right? That's the severity, is the ultimate price. The severity of arc flash could be death as well as burns, severe burns, all that jazz. And likelihood, though, how do we determine likelihood? I want to talk about that as well, because statistics help us understand likelihood. Very important piece of the risk puzzle. So you can sign up for their newsletter and all of the great stuff that the ESFI has to offer. Now, again, I would say that if I were in your shoes, I would want to make sure that when I speak with our electrical, when I speak with homeowners, when I speak with owners of or anybody in other trades, they don't have to be the electrical trade, because 70E tells us that more people get injured and killed that are not electrical professionals, right? So it's the plumber who's on the site. It's the carpenter who's on the site. It could be the cleaning person. It could be the delivery person. And if it's a residential application, it could be any of the occupants or anybody who's visiting. It could be children. So we want to raise awareness around recognizing the hazards. I think that's a very key piece of the puzzle. So we're going to talk about shock. Again, I put some links down. The first link that I put there is from ESFI, which is their page dedicated and focused on Electrical Safety Month. Now, ESFI also puts out statistics, and they'll tell you that there were 126 fatal electrical injuries in 2020. Now, look at this trend. This is an interesting trend. You'll see electrical fatalities are the blue line, and then the orange line is all ownerships hours worked. So as what you're seeing is hours worked going up, and you're looking at shock. It seems to come down, or electrical fatalities seems to come down, and it's rising back up again. But in 2020, it took a dive. But look at how the trend of electrical fatalities follows hours worked. What happened in 2020? What was significant about the year 2020? That is when we went into lockdown because of COVID. So you didn't have as many hours worked, and you didn't have as many injuries. So it would seem that that injuries, and when injuries on the job site, regardless of the category, is going to follow the number of hours being worked. If you're not on the job site, you can't get a claim on the job site. Now, this is just workplace electrical injuries. So this doesn't account for what you might find in the Consumer Product Safety Commission. And in many cases, there's still a lot of data points that aren't reported, right? So just some data to think about. Occupations involved in electrical fatalities. Look at that. It's construction and extraction, installation, maintenance, and repair, building and grounds cleaning and maintenance. It's not just the electrical worker who's getting hurt. Transportations and material moving, management, farming, fishing, forestry. The mining industry has had the highest rate of fatal electrical industry injuries, followed by construction. So again, you're seeing the electrical injuries are in black. This is electrical injuries versus total hours worked. Now, over here, there's electrical injuries are showing that they went up in 2020 and the hours worked went down. Let's take a look at that previous slide. These are electrical fatalities. So here's the difference. So this one is a trend of fatalities. This one is a trend of electrical injuries. There's a big difference. So as during COVID, the hours worked went down, but our injuries went up. And I wouldn't want to hesitate to make assumptions. So I'm not going to offer any in my opinions on that. You can think about your own opinions on why that may or may not have occurred. All right. Now, here's another interesting trend. This actually is from a report, and I believe it was the Census of Fatal Occupational Injuries, which I have the link down below. There's a few. I have the links I have down below. Let's just talk about that real quick. So the links that I have down below, I've got the Census of Fatal Occupational. I can't talk. Census of Fatal Occupational Injuries, and this from the BLS. I have NIST Guide for Conducting Risk Control, because we're going to be talking risk, and that I believe is a free download. Electrocutions associated with consumer products from 2004 to 2013. These are statistics. And then there's fatalities from contact with electricity in construction. And this is from CPWR. I got to look at what that is. CPWR. Let's take a look. Construction chart book, the Center for Construction Research and Training. That's what that is. Center for Construction Research and Training. So I have a link to that down below, and you can take a look at that at your leisure. And why do I provide some of this data? It's because we have to understand likelihood, right? And I've told people before, we get into a vehicle. We get into a vehicle and we drive to work, we drive to school, we drive to church, we drive wherever we're going to go. We accept a level of risk, right? And we do things to reduce our level of risk. Statistics, though, will help us understand the likelihood of something occurring. There are statistics of accidents on the highway. There are statistics of accidents at intersections. There are statistics of accidents in parking lots, right? And I just went through a training session from my company with regard to driver safety, and they tell you that, intersections pose a challenge because of everything that's going on. Parking lots pose a challenge. So your chances go up and down based upon what it is you're doing. And we understand those areas based on statistics. And what do you do when you're going to be in an area where you have a high likelihood or a higher likelihood of something bad going on? You pay attention, you follow the rules, you do what you need to do to avoid a problem, so you don't experience the severity. So we look at statistics, and it helps us understand likelihood. We look at the technical details around arc flash and the hazards. That helps us understand severity. All right. So let's continue our discussion. Let's talk about the electrical hazard. Now, the NFPA 70E tells us that we have four hazards that we have to think about. 4 electrical hazards. We have shock. That's when current passes through the human's body nervous system or vascular system or across the surface of the body. We have arc flash. Arc flash are your very high temperatures. What do we have? We have current flowing through a plasma arc. It's flowing through air, for goodness sake. And we understand that the magnitude of that current and the duration of that current play a significant role in establishing the amount of heat that you will see and experience in an arc flash event. Arc blast, when an event occurs, and we've all seen the videos, when an event occurs, we see that pressure wave hit the subject, or hopefully it's just a dummy, a mannequin that's put in front of a piece of equipment, and we watch the mannequin fly back or fall over. We watch the clothes break open. There are many different tests that are conducted to understand arc blast. There's no way to calculate arc blast. Absolutely no way to determine the amount of force. There's no equation that we use to determine force. When we calculate arc flash, the only thing we are calculating is the amount of heat. We are not calculating the force that you will feel or that may project you against a wall or into other equipment. All that we calculate when we calculate arc flash is heat. Arc blast is another consideration. And then you have thermal burns. These are burns that, if you look at the definition within 70E and how they define what are conducted by a thermal burn, they're looking at what might not be a shock hazard, what might not be an arc flash hazard. If I have current flowing through an object, steel or whatnot, I may not get electrocuted by it because the currents are too low, or the voltage is too low. Rather, the voltage is too low. It's not going to be enough potential to push that current through my body and put me into defib, but it could heat the enclosure up. It could heat the equipment up to a point that when and if I touch it, I can receive a thermal burn. All right. Now, let's talk about risk. And I mentioned this word, and I'll tell you what, all week, all this month, just focus on these two things. Look at whatever it is you're doing. If you're designing a power distribution system, if you are going to get into your vehicle, if you are going to operate a piece of equipment, if you're going to be at home and you're going to operate your lawnmower, change the fuel in your lawnmower, change the oil in your vehicle, everything you do this for the month of May. Look at what you're doing through the eyes of likelihood and severity, right? You're going to use a table saw. You're going to be in your garage and you're going to use your table saw to, cut a piece of wood. And you have an open blade there and you're going to push wood through the blade. What's the likelihood that you may go into that blade with your hand? What's the proximity? You can reduce the likelihood by getting as far away from that blade as possible. You can reduce the likelihood by using a stick to push that piece of wood through the saw blade. And what's the severity if you didn't? You can lose digits, right? You could suffer, and if you're on medication and it's blood thinner medication, you could lose an extreme amount of blood you take off of a digit, right? So there are a lot of severity may be different for each individual, obviously, but think about everything you do. And if you're designing a power distribution system, think about the likelihood and severity. We talk about arc flash, incident energy, that first panel board on the secondary of every transformer. Think about that panel board on the secondary of every single transformer. What is the incident energy at that location? And can you address severity at those locations? Because the likelihood of doing justified energized work is higher. If you have a transformer feeding a motor, feeding a piece of equipment, an industrial control panel that is probably going to have an electrical worker exposing themselves to hazards because they're doing troubleshooting. Can we control likelihood by changing the design? And can we control severity by thinking about things differently, reducing the incident energy by putting means in to do that? Putting barriers in, separating equipment so that they can establish an electrically safe work condition and have absolutely no energized parts inside of a piece of equipment. We need to think about what we do, especially in the electrical industry, through the eyes of risk. And we need to educate all of the decision makers who are going to fund the reduction of risk, the reduction of likelihood and severity in their power distribution systems. Because in my opinion, much of this goes above and beyond requirements of the National Electrical Code. Now, NIST, this is the document that I shared with you. And I have some quotes out of this document. It's a free download. It's a guide for conducting risk assessments It's from the National Institute of Standards and Technology, the U.S. Department of Commerce. Because the taxpayers paid for this, it is brought to you for free, and it's information you need to use, leverage, and use it and abuse it, okay, to a point. All right. So what do they understand likelihood as being? Likelihood of occurrence is a weighted risk factor based on an analysis of the probability that a given threat is capable of exploiting a given vulnerability or set of vulnerabilities. So they're trying to help you understand, if you have an exposed conductor, you're going to get into a panel board. You're going to turn the main off, and you're going to see energized lugs at the line side of that main overcurrent protected device. And now you're going to push wires down through the top, right past those energized conductors. Do you think the likelihood of coming in contact with those accidentally is increased? Probably. Do you think that if you put a barrier there to reduce that likelihood, that would be a good thing? Probably. Is it a code requirement? Yes, for service entrance equipment. Looking at expanding these barrier requirements, buying finger-safe solutions as opposed to non-finger-safe solutions. Do you think that will reduce the likelihood of an occurrence? Then the risk factor is what? You're staring at maybe 480 volts or 240 volts or 120 volts. All of that can kill you. So, likelihood. Assess the likelihood that threats, events will be initiated or will occur. Assess the likelihood that the threat events, once initiated or occurring, will result in adverse impacts or harm to the organizational operations, assets, individuals, or the nation. Assess the overall likelihood as a combination of likelihood of initiation occurrence and likelihood of resulting in adverse impact. Again, from the NIST document. Then there's uncertainty. They define uncertainty. Inherent in the evaluation of risk, limitations on the extent of which the future will resemble the past. So, you have to think about you don't know what you don't know, right? You can say, I have an individual who has been safe all his life and he's done this work all his life, so there's chances of him doing something wrong is little to none. But if you're not controlling that risk, if you're not controlling that likelihood, you have no control over the outcome. You can't base the future off of the past in many cases. Now, we look at statistics. We can say the statistics show, and that's the past. Could that predict the future? May or may not. You may say, look, all of the statistics say that that when I get in my car and I drive to work on this specific highway, that I should end up getting in an accident, and I haven't in 20 years. Well, the statistics didn't prove true for you, but they may prove true for someone else. So you have to understand the threat and the adversities, including all of your tactics and techniques and procedures, because you may drive very differently. You may have equipment in your vehicle that gives you better visibility. You might be in a vehicle that gives you better visibility than other vehicles. There's a lot of different data points. You may go to work and you're very well rested because you always get your 6-7 hours of sleep every night. And that may play a role in why other accidents occur. But you don't know that. We don't know that. So what we'd have to do is we have to understand that uncertainty is inherent in the evaluation of risk. Then you estimate the probability of each possible accident based on past history and industry benchmarks. And that's why the statistics play such an important role. You can't make assumptions not based on statistics. You can look at statistics and have an opinion. We all have opinions, right? You can look at a set of statistics and say, in my opinion, the reason those are high is because of X, Y, and Z. Someone else may have a completely different view on that. So all you can do is take the data for what it is and make your decisions based on around likelihood. This is the hardest part, in my opinion, is likelihood. Severity, I can understand severity. It's something I can show you a video on. I wouldn't want to show you a video of somebody getting shocked, but there are videos of showing you people accidentally getting electrocuted. So you can understand severity. We have research to understand severity. We can demonstrate arc flashes and burns. It's hard to determine likelihood. Can be defined in terms of occurrences per units of time, events, population. This is all about data, right? You can slice and dice data however you would like, but you have to think about what is your goal. Are you slicing and dicing data to reduce cost? Are you slicing, dicing data to sell a product, to sell a solution, to sell your services? You got to be really careful about the information and data. Likelihood of the electrical hazards, statistics of shock, and statistics of arc flash. That's what we fall back on. So we have to. And if we go to NFPA 70E and 130.4 for the shock risk assessment, it tells you to identify the shock hazards. So that's the first step. You've got to identify shock hazards. You have to estimate the likelihood of coming in contact. And then you have to determine all your personal protective equipment. Now, I believe it's Annex K of 70E, tells us the data. 98% of fatal occupational electrical injuries are electrical shock injuries. Think about that. 98% of fatal occupational electrical injuries are shock. Now, when you take and you get a 70E class, a lot of people love to focus on arc flash. Arc flash isn't the number one killer. Arc flash is bad. You don't want to experience an arc flash. But this is what kills people in our electrical industry. You can't see it. You don't know that it's hot, energized. You don't know. And when you don't know, mistakes can be made. When we talk about the qualified person, we say, well, that person wasn't qualified or shouldn't have been using the equipment that way. We can make design changes to even help the unqualified person, because Annex K tells us electrical injuries represent a serious workplace health and safety issue to electrical and non-electrical workers. So that person may not have been qualified to do work on electrical equipment because maybe they were a plumber, maybe they were a architect, maybe they were a carpenter, or just a delivery person. But they were electrocuted and they were killed because they could not understand and recognize the electrical hazards. We have to think about the non-electrical workers. Annex K helps us understand that. They also help us understand that electrical incidents, once again, found to involve a large share of non-electrical workers, with approximately 1/2 of incidents involving workers from outside electrical crafts. So that tells you, when you think about the design of a power distribution system, if you think about the design of products and solutions and arrangement, it's not just the qualified worker we have to think about. It's also that, I'll say, unqualified for electrical stuff, but qualified for whatever it is that they were there to do. Plumbers are great at their trade. If they're not trained in electricity, if they're not trained to understand and recognize electrical hazards, then they're not qualified to do the electrical side. Do you think our paths cross on a construction site? Absolutely. Do you think our paths cross throughout the life of a structure, whether it is residential or commercial or industrial? Absolutely. And we need to think about that. Over 30,000 non-fatal electrical shock accidents occur each year. Non-fatal shock accidents. Now, those are bad. Let me tell you why. They have this thing called close calls, right? And there's a philosophy that I can, if I have X amount of close calls, eventually someone's going to get it. and it's going to be catastrophic. Another thing is I was just at the electrical safety workshop down in, I think it was Jacksonville, Florida. And that event was interesting. There was a presentation by an electrician who was suffering from the hazards of constantly, many times in his career, he was shocked, not electrocuted. He wasn't killed. He was shocked. Current passed through his body because of the unjustified energized work that he was performing. All right. He, in his presentation and in his discussion, I listened. I just listened to his presentation. I listened to him answer questions, and because I'm thinking, you know, what is it he's trying to say? He survived, right? He survived a shock. And was his message supposed to be that, you know, eventually I'm going to get killed, or I was going to get killed? No. His message was around a fundamental that many of us forget about when it comes to shock. What do we always do when we talk electrocutions? We talk about current passing through the chest cavity, right? We talk about hand to hand, and we talk about this chest cavity and your heart and how it can stop your heart from pumping. His message was confirmed by our keynote speaker at that event, who was a doctor researching this. When we talk about ground faults, we talk about current passing. What do we say? You have an equipment grounding conductor, right? And we say, what path will current take back to the source? And some people will say, well, that's why we have the equipment grounding conductor. And then the person who's doing the class, because they set you up, will say, no, current takes all paths back to the source, right? Because parallel circuits, because we understand the fundamentals of electricity. We do as electrical professionals, that current divides and goes to many different paths. Some paths a little bit more than others. Well, what this gentleman's message was, that current didn't just go through his finger. Current didn't just pass through the elbow and his hand. Current took all paths, which includes every part of your neurological system in your body and your brain. And he was suffering from that. And the doctor who did the keynote said, with evidence, and he showed videos of individuals who, there was one lady who received many shocks over her career. And she was going to doctors, and she did not understand what was going on, and nobody could describe this. But this doctor who's researching this I don't know what I would call it, medical condition, is researching this. He's recognizing that what he demonstrated with this one individual happens to many. He asked her to walk across the floor towards him, and he videotaped it. She walked across the floor. Then he tells her to go back again. And now I want you to close your eyes and walk to me. And she could not, the moment she closed her eyes, she could not keep her balance. The shock and all of those small currents going through her body all those years impacted her neurological system. And I hope I'm saying that right. It's neurological. So it's all of those paths that, and all of those, the tissue and all of the nerves and whatnot that were damaged due to repetitive nature. So we may say that 30,000 non-fatal electrical shock incidents occur each year, and say, well, it's non-fatal. So, you know, and we can liken that to likelihood that, you know, eventually it's going to get you. But 30,000 There are people that are getting repetitive shocks through their body, current passing through their body, even if it's through the fingers. Because you're a circuit, and your body presents many parallel paths. We don't think about it. We think about, I've heard electricians tell me, if I go like this, current goes through this finger and through that finger, and it's a small circuit. Electricity doesn't work that way. Electricity takes all paths, including all paths through your body when you touch conductors with these two fingers. And there were, historically, that's how many in the industry operated and functioned. I witnessed it myself. And they said, oh, I'm perfectly fine because of this. But there are people that suffer years after the fact due to numerous occasions of current passing through their body. So keep that in mind. And I'm sure we're probably going to see more on that in the future as this doctor continues his research and presents his data. Okay, so now in estimating the likelihood, in 130.4 of NFPA 70E, they tell us that the design of the electrical equipment makes a difference, and the operating conditions and condition of maintenance makes a difference. So this sort of gets you into the whole discussion of a qualified person. And in many cases, you may say, I'm qualified. You may say, look, Tom, I'm qualified to work on this equipment because I design motherboards. I work with computers every day. But you don't know this piece of equipment. You don't know what the voltage level is on this door. You don't know what the voltage levels are in anything in there. Is it 120? Is it 240? Is it 20 volts DC, 15 volts DC? Is it 10 volts? Is it 5 volts DC? You don't know because you're not qualified. Is it safe? You don't know. Can you be hurt? You don't know. Because you have to understand this equipment. And when you get into larger equipment, power distribution systems that get very complicated, think about these products that have displays on them. There's probably UPS equipment inside. If you don't understand this equipment, and it can get complicated pretty doggone quick. If you're a panel board kind of person and that's what you've worked on, this is far, you may say, yeah, that's a panel board. That's a panel board. Well, what's in here? Well, looks like a transformer to me, and it is. It's a transformer. What about all these displays? What's powering those up? How much voltage? What's inside this equipment? If you don't know, then you're not qualified. Now let's talk about the shock hazard, all of that to finally get to this. Shock hazard in NFPA 70E defines a shock hazard as a source of possible injury or damage to health associated with current through the body. And what is it caused by? Caused by contact or approach to exposed energized electrical conductors. And we saw some exposed electrical conductors right here, right? Chances are that's pretty high voltage. Relatively high. I could say it's if your life is dealing with 24 volt DC, that's high voltage, right? But we consider it low voltage as 480 volts. What's the voltages of here, of this equipment, right? So the shock hazard tells us that in an informational note, injury and damage to health resulting from shock is dependent upon the magnitude of electric current and the power source frequency, and the path and time duration that it passes through the body. And it changes your, it has a, it can impact you in more ways than you think, right? It passes through your brain, because remember, current takes all paths through the body. Yes, we all worry about the heart going into defib because that's immediate death, relatively speaking. But what about the long-term effects of shock? Surviving a shock can have long-term effects on organs and other areas within your body. Now, magnitude. And we say magnitude matters. Now, what 110.3 tells us is that energized electrical conductors and circuit parts operating at voltages equal to or greater than 50 volts. So right now, in 70E, 50 volts, AC or DC, is the line in the sand. 50 volts or more. You have to put that into an electrically safe work condition. Why is that? Because your body has a resistance, an impedance. And what equation determines how much current flows? V equals IR. So voltage divided by resistance gives you your current. And we know 4 to 6 milliamps is not defib. That's a big misconception. 4 to 6 milliamps, 6 milliamps and above is not the defibrillation. 6 milliamps is let go. Okay, your body can take more than 6 milliamps and not go into defib. And again, it depends on your health, obviously. But we here in the United States worry about we worry about let go. In other countries, they worry more about defibrillation. So their thresholds may be higher than 4 to 6 milliamps. Their clearing times will still be lower than what will put your heart into defib. But we want you to be able to let go of the conductor. And that's what the current and clearing time of solutions seek to achieve. All right, so 50 volts shall be put into an electrically safe work condition. That's in 110.3. 110.4 talks about energized work. Equipment operating less than 50 volts, they give you some rules because they recognize it's not just the shock hazard that you got to think about. They say energized electrical conductors and circuit parts that operate less than 50 volts shall not be required to be de-energized. But they add this other language where the capacity of the source and any overcurrent protection between the energy source and the worker are considered, and it doesn't expose you to electrical burns or explosion due to electrical arcs. All of that's important. $50 volts seems to be the number. Okay, now when we get to, we want to provide protection to the human person. The definition of a GFCI. So anytime you see the use of the term ground fault circuit interrupter, you're talking a Class A device. What is a Class A device? The informational note tells us. Class A ground fault circuit interrupters trip when the current to ground is 6 milliamps or higher and does not trip when the current to ground is less than 4 milliamps. Now, 6 milliamps or higher. That means that if I do the math and I calculate current through your body to be 20 amps, because of the voltage, because of the current, because of the impedance, if I calculate 20 amps that will pass through your body will see 20 amps even if you're on a GFCI receptacle or circuit breaker. Doesn't matter. Your body is going to see 20 amps. But those devices will clear it fast enough that it will not let your heart go into defib, but it will also let you let go of the conductor or part. Now, Class A versus Class B, we don't make a Class B anymore, but there's a Class C, D, and E, which is the special purpose GFCI. So that's a product that just recently, the special purpose GFCI was just introduced into the National Electrical Code for the 2023 cycle. So we're going to have a definition of a special purpose GFCI, which does belong under the UL 943 standard, but operates off of more of the concept of defib as opposed to let go, because it addresses a higher voltage. More about that maybe during Electrical Safety Month. Let's talk about how, say, the contents of a GFCI receptacle. Many people don't realize this. But the CT inside of a GFCI receptacle is before the blades where you plug something in and before those load terminals. So anything connected to those load terminals is also provided GFCI protection. But what it can't do is look behind it, right? So I've heard some people say, hey, I had a problem with my circuit and it kept tripping the circuit breaker. So I put this receptacle in and it held. But very well could be that the problem is between the receptacle and that thermomagnetic breaker. In my case, in my panel board, I had all my panel boards in my basement on the wall here, and I have an alarm system, and I was moving, I think I was replacing a battery in my alarm system. And I moved those conductors that go into the panel board. And I think it went into the side, if I'm not mistaken. No, it went into the top. Can't remember why I was up there, but I moved a conductor and a breaker tripped. I have all GFCI breakers. And my GFCI breaker tripped, and I couldn't figure out what happened. Then I learned that when the electrician put the conductor through that into the panel board, and they clamped down on that wire, they damaged the conductor, cut the insulation. And when I moved the wire, I came in contact with my enclosure. So if I would have had a GFCI receptacle downstream, it's not going to look behind it. If I would have had and a GFCI circuit breaker is not going to look upstream either. So you got to be a little careful with regard to understanding the technology and understand what it is and isn't telling you. Now, the receptacles will protect everything downstream, including the installed wiring for ground faults, and anything connected to any of the blades for any of the standard receptacles that are fed from and through this receptacle. Provide a lot and significant protection for everything downstream. But remember, that CT, it's only looking for what's going out and coming back. So what goes through that CT has to come back through that CT. GFCI circuit breakers operate in the same fashion. Okay, so here is a GFCI circuit breaker. What goes through that CT has to come back through that CT. If it goes anywhere else, it will trip, but it doesn't look behind it. None of these devices can look behind it because it's all about this sensor. That quote unquote donut makes a big difference. Now, if you use the push to test feature, what the push to test buttons do is it sends current through, but around the sensor. And it works the same for both the GFCI receptacle and a circuit breaker. Now, I've had people tell me too, you got to be careful if you have a tester on a receptacle where there is no equipment grounding conductor. I don't know if that's true or not, but that's what I've heard. So you have to understand the technologies, you have to understand the capabilities of the equipment. I'd love to hear your chat. I'd like, chat down below. How do you test your breakers? And how do you test your GFCI receptacles? Do you test monthly these receptacles and circuit breakers? You have to press that button. Do you press the button? I recently tested my receptacle in the last hotel I was in, and it did not reset. And I couldn't figure out why. I tried multiple times now. It looked like somebody had put toothpaste on it. I don't know. It was in the bathroom, but it did not reset. Test your receptacles and your circuit breakers to make sure they are functioning and operating correctly. You can also get the plug-in portable GFCIs, and it's the same technology. It has a sensor. You have a current sensing device, you have an equipment grounding conductor, you have a neutral, and you have a hot. That sensor is a very important piece of the puzzle, and this is your plug-in portable GFCI. So there's a sensor in there. There's a donut, and the current that goes through the donut has to come back. And if there's a difference, then it trips. A difference of what? somewhere starting at 4 to 6 milliamps. That's the pickup point, right? That's when it decides to open, but it can be a lot more current passing around that sensor. Now, GFPE, and I've heard a lot of people say ground fault protection, that's what I provide, ground fault protection. And they may mean GFCI, but they're not saying GFCI. Our terminology and our language is important. So GFCIs and GFPE, ground fault protection of equipment, two different things. One is listed to 943 and the other is listed to 1053. Ground fault protection of equipment, the actual pickup point is determined by the manufacturer or the engineer who sets the setting. Think about ground fault protection of equipment. Its service entrance equipment is the same as ground fault protection of equipment on that de-icing 20 amp, 15 amp circuit that you have. It's all listed to the same standard. They all have to follow the same rules. So I can have GFPE set at thousands of amps, or I can have ground fault protection of equipment set at milliamps. Depends on the application. And there's nothing in the National Electrical Code that references 30 milliamps for GFPE for de-icing. Where we do mention 30 milliamps, and now 100 milliamps is around marinas. And what did we do in marinas? And that's going to be a whole nother session for Electrical Safety Month here on IAEI News Live. I got to get Donnie Cook to help me with a live session on ground fault protection of equipment at 100 milliamps on feeders, 30 milliamps on shore power, and then we did 4 to 6 GFCIs on receptacles. But we did a tiered solution for marinas to identify an aging infrastructure. The 100 milliamps is not going to stop a body from going into defib. It's not going to stop you. It's not going to let you let it go. But it will identify a problem, hopefully before you touch it. But there is a difference. One is personnel protection, UL 943, and the pickup is somewhere between 4 to 6 milliamps, and the trip times are approximately 15 milliseconds. And then the 1053 device, it has ground fault and sensing relaying equipment leakage within 10% of the level defined by the manufacturer. Now, if I'm thinking about, I mentioned defib and I mentioned let go, the UL standard recognizes that red curve. Heart fibrillation threshold for normal healthy adults. So look at this. This is 0 amps all the way over there, all the way up to 260 milliamps. And it shows you that your heart, that you can take 260 milliamps for upwards of 0.2 seconds for a healthy individual. But the UL line is right here. This is the UL line. And this is how a Class A GFCI actually operates in the clearing time. Much faster than your heart going into defib and much faster than the UL required permitted maximum clearing time. Now, that may vary by manufacturer. A manufacturer of a GFCI may hug this curve a little bit closer to avoid what? Nuisance tripping due to various loads. But typically, you're going to see a very fast-acting device. All right. Now, shock. So what do we know? What do we know about shock? We know that 50 volts is the threshold. We know that a ground fault circuit interrupter is designed to keep you alive, right? We know that ground fault protection of equipment is just that. It's protection of equipment. The clearing times and the pickup times are not established as rigorous as GFCI. So, shock protection can come in the form of a GFCI. Shock protection can come in the form of barriers and not coming in contact. What does 70E? 70E tells us we have a shock boundary. And for certain voltages, they'll tell you don't come in contact, period. 120 volts, residential work, they just tell you avoid contact. So that could be putting barriers in place that can be obviously establishing an electrically safe work condition, wearing gloves, rubber. Don't wear just leather gloves. Remember, you need to have gloves that are rated, and you want your leather outers to protect the gloves. And we're going to have a discussion this month around Electrical Safety Month on gloves as well, your personal protective equipment when it comes to shock. I'd like to focus on shock. That's my opinion. What is out there for shock? Because it's like the number one killer in our industry. We saw the statistics, and the statistics are real. The numbers are real. So we have to pay special attention for those applications for that electrical hazard. All right. Remember, this month, this is Electrical Safety Month. Next week, I believe, I'm just going to double check, but I believe next week is our Siemens. We'll be working with Siemens. Let me switch my account here for an IAEI News Live on arc fault circuit interrupters. Let's go to content, go to live, and there it is. They have a first to market discussion. Now that ought to be interesting. I have some links in the YouTube site for next week, and it is, let me just make sure it's next week. I came in here to look at the date. May 17th. I believe that's next week, 12 o'clock p.m. I will have Ashley with me, Ashley Bryant from Siemens, and we're going to learn some of those latest, but we're also going to talk about some of the code requirements, and I'll share with you some of the stuff that's going on with the National Electrical Code, the 2023 version of the NEC, some of the new stuff that's coming down the pike. And that's what I have for that. That's next week. We're going to have I'm going to be hopefully I'm going to grab Donnie Cook, and we're going to get a session with Donnie talking about marinas. And I'll try to bring as many different individuals, but this is Electrical Safety Month. We should always be thinking about electrical safety, but especially this month, let's use this time to share with others. We're on a journey to change our culture. It begins with each of us. It begins with you and me. That's our job. We're the electrical professional. We are aware, we are knowledgeable, and we need to share that knowledge with others in other trades, homeowners, building owners, everybody. Let's raise awareness for electrical safety. Let's think about that. All right. Well, that's all I have for this one, for this session. Hopefully you got something out of it. I hope you enjoyed our discussion as I did. And we will see you next week for another IAEI News Live. Thanks for what you do for the electrical industry. Thanks for what you do for electrical safety. Remember to stay safe and please stay healthy. See you next week.